On August 6, 2012, the Mars Curiosity rover touched down in Gale Crater, carrying the most sophisticated drilling equipment ever sent to another planet. Its mission: to search for evidence of past life by analyzing rock samples from beneath the Martian surface. For 7 years, Curiosity drilled systematically, collecting samples, studying composition, sending data back to Earth. Then, on September 24, 2019, everything changed. The rover had positioned itself at a promising drill site designated Glen Etive 2, a location chosen after months of careful geological survey. Instruments indicated unusual subsurface density anomalies. Spectroscopic readings suggested rare mineral concentrations. Every parameter pointed to scientific gold. Curiosity began drilling at 1432 UTC. For 47 minutes, telemetry streamed back to Earth normally. Drill depth, power consumption, vibration data, all within expected parameters. Then, at 1519 UTC, the data stream changed. Drill resistance increased dramatically, power consumption spiked, and the rover's onboard computers detected something that shouldn't exist beneath the Martian surface: a hollow cavity. For the next 47 hours, Curiosity transmitted continuous data to Earth. Not routine telemetry, but massive volumes of imaging, spectroscopic and chemical analysis from the drill site. The data packages were so large that NASA had to dedicate additional deep space network resources to capture them all. Then, abruptly, the transmission stopped. When contact resumed 3 days later, Curiosity had moved to a completely different location. The drill site at Glen Etive 2 was never mentioned again in public mission updates. What did Curiosity find beneath the surface of Mars? Why did NASA abandon one of the most promising drill sites of the entire mission? And what's hidden in the 47 hours of data that has never been publicly released? If you're ready to discover what's really buried beneath Mars's surface, stay with me, because what Curiosity found that day challenges everything we thought we knew about the history of the red planet and who or what might have walked its surface long before humans ever gazed at it through telescopes. Gale Crater is a 154-kilometer-wide impact basin that formed approximately 3.8 billion years ago. At its center rises Mount Sharp, a 5-kilometer-tall mountain of layered sedimentary rock that preserves billions of years of Martian geological history. Curiosity has spent years climbing the lower slopes of this mountain, drilling and analyzing samples that tell the story of ancient Mars. The Glen Etive region, located on the mountain's northwestern flank, caught scientists' attention in early 2019. Orbital observations from the Mars Reconnaissance Orbiter showed spectral signatures suggesting high concentrations of clay minerals, indicators that liquid water once flowed abundantly in this area. Dr. Ashwin Vasavada, Curiosity's project scientist at NASA's Jet Propulsion Laboratory, described the site selection in a March 2019 mission update. Glen Etive represents one of the most promising locations we've identified for understanding Mars' past habitability. The mineralogy is complex, the stratigraphy is well preserved, and our ground-penetrating radar suggests interesting subsurface structures. That phrase, interesting subsurface structures, would prove prophetic. Curiosity's ground-penetrating radar, called RIMFAX, Radar Imager for Mars Subsurface Experiment, had been scanning ahead of the rover's path. At Glen Etive 2, RIMFAX detected something unusual: a void space approximately 3 meters beneath the surface, roughly 2 meters in diameter. Natural voids can form in sedimentary rock through erosion or gas pockets, but this cavity showed characteristics that puzzled the science team. Dr. Sarah Chin, a geophysicist at the Southwest Research Institute who analyzed the RIMFAX data, noted the anomaly in her research logs. The void's geometry is too regular. Natural cavities show irregular boundaries reflecting the random nature of erosion. This feature showed near-perfect circular symmetry and horizontal cross-section and appeared to have a flat floor. The radar returns suggested the cavity might contain material with different electromagnetic properties than the surrounding rock. The decision to drill at this location was made after weeks of debate. Some team members worried about potential damage to the drill system if it broke through into a cavity. Others argued that discovering what lay inside the void was worth the risk. The scientific potential won out. Curiosity's drill system is a marvel of engineering. It can bore up to 6.5 centimeters into Martian rock using a percussive rotary technique, simultaneously rotating and hammering to pulverize stone. Sensors monitor every aspect of the drilling process: bit rotation speed, applied force, power consumption, temperature, and drill depth. On September 24, 2019, at 14:32 UTC, Curiosity began drilling at Glen Etive 2. The initial penetration proceeded normally. The drill bit chewed through the top layers of sedimentary rock at expected rates. Power consumption remained steady. All parameters were nominal. At 15:07 UTC, 35 minutes into the drilling operation, sensors detected the first anomaly. Drill resistance dropped suddenly as if the bit had punched through into empty space. This matched predictions from the RIMFAX data. The drill had reached the cavity. Standard protocol called for stopping at this point to analyze the situation. But according to mission logs obtained through Freedom of Information Act requests, ground controllers made an unusual decision. They commanded Curiosity to continue drilling through the void and into whatever lay below. Dr. Marcus Webb, a materials scientist at Caltech who has analyzed the publicly released drilling data, found this decision perplexing. Drilling through a void risks damaging the drill bit when it strikes the far side of the cavity. The bit could shatter or bend, yet controllers pushed forward aggressively, even increasing the drill's power setting. They clearly wanted to reach whatever was below that void, and they wanted it badly enough to risk the mission's drilling capability. At 15:19 UTC, the drill broke through the bottom of the cavity. What happened next defied all expectations. Drill resistance increased by a factor of 300%. The bit had struck something far harder than the sedimentary rock surrounding it. Yet the material didn't shatter or crack as rock would. Instead, sensors detected smooth, continuous cutting, as if the drill was boring into metal or ceramic. Power consumption spiked to 94% of the drill system's maximum capacity, far higher than any previous drilling operation. Temperature sensors at the drill bit recorded values 40 degrees Celsius above ambient, suggesting friction with an unusually dense, hard material. And then came the most anomalous reading of all. The drill's vibration sensors detected a resonance frequency of 2,047 Hertz emanating from the material being drilled. This frequency matched no known natural mineral, but it did match the resonant frequency of titanium alloys commonly used in aerospace engineering. The moment Curiosity's drill bit penetrated the hard layer beneath the cavity, the rover's scientific instruments went into overdrive. Without any commands from Earth, operating on pre-programmed autonomous protocols, Curiosity began the most intensive data collection sequence of its entire mission. The Alpha Particle X-ray Spectrometer, APXS, activated, analyzing the chemical composition of the drill cuttings. The chemistry and camera ChemCam instrument fired its laser repeatedly at the drill site, vaporizing tiny amounts of material for spectroscopic analysis. The Mars Hand Lens Imager, MOSLI, captured thousands of extreme close-up images, and Curiosity's main cameras documented everything from multiple angles. Dr. Jennifer Torres, a data systems engineer who worked on Curiosity's autonomous science protocols, explained the significance. The rover's AI is programmed to recognize potential biosignatures or unusual geological features and respond with intensive investigation. For the system to trigger a full autonomous science campaign, it must have detected something extraordinary, something that met multiple criteria for anomalous findings. The data began streaming back to Earth in massive volumes. Mission Control logged telemetry packages totaling 3.2 gigabytes over the next 47 hours, approximately 50 times the normal daily data transmission from Curiosity. The Deep Space Network had to allocate additional antenna time to capture it all. What was in that data? NASA has released only fragments, carefully selected images and spectroscopic readings that show interesting mineralogy and complex chemistry. But researchers who have submitted FOIA requests for the complete data set have been denied, with NASA citing ongoing analysis and preliminary data requiring validation. Dr. Kevin Patel, an astrogeologist at the University of Arizona, has spent 3 years attempting to access the complete Glen Etive 2 data. I've requested every drilling data set from Curiosity's mission, and I've received all of them, except this one. NASA claims the data is still being processed, but it's been 6 years. Either there's a massive backlog affecting only this specific drilling operation, or something in that data is being withheld deliberately. The fragments that have been released reveal tantalizing clues. ChemCam spectroscopy detected elemental signatures inconsistent with any known Martian mineral. The spectrum showed absorption lines corresponding to refined metals, iron, nickel, chromium, and what appeared to be titanium in concentrations and ratios, suggesting alloy composition rather than natural occurrence. Even more intriguing, isotope ratios in the drilled material showed deviations from Martian baseline values. On Earth, industrial processes create characteristic isotopic fractionation, the preferential use of lighter or heavier isotopes that leaves a signature distinct from natural materials. The Glen Etive 2 samples showed exactly this type of fractionation. Among the limited data NASA has released, one set of MOSLI images has sparked intense debate. The extreme close-up photographs of the drill cuttings show microscopic spheres mixed with the powdered rock. These spheres are remarkably uniform in size, approximately 50-100 micrometers in diameter, and appear perfectly round. Some show surface features suggesting they were manufactured rather than formed through natural processes. 2 regular dimpling patterns, what appear to be seams or joints, and in some cases, what look like microscopic surface textures or markings. Dr. Chen performed detailed analysis of the sphere images. The size distribution is too narrow for natural formation. When geological processes create spherical particles, like concretions or impact glass beads, you get a wide range of sizes following a statistical distribution. But these spheres cluster tightly around specific diameters, suggesting quality-controlled manufacturing. Natural processes can create spherical particles on Mars, Blueberries, small hematite spheres formed by mineral precipitation in water, have been found elsewhere by Mars rovers. But those blueberries show size variation, irregular surfaces, and composition consistent with simple iron oxide minerals. The Glen Etive 2 spheres are different. Spectroscopic analysis revealed complex composition, metallic cores, surrounded by ceramic or glass-like shells. Some spheres appear to contain internal structures, voids or chambers visible in the highest resolution images. What we're looking at resembles microencapsulation technology, Dr. Patel observed. On Earth, we manufacture microspheres for drug delivery, industrial catalysts, and advanced materials. These appear structurally similar, engineered particles designed for specific functions. The most controversial aspect of the spheres involves their distribution. They weren't uniformly mixed through the drilled material. Instead, they appeared in discrete layers, as if they'd been deposited or placed deliberately rather than forming naturally within the rock matrix. Statistical analysis revealed another anomaly. The spheres showed a trimodal size distribution. 3 distinct populations clustered around 50, 75, and 100 micrometers. Natural processes typically produce unimodal distributions, one peak size with variation around it. Multiple distinct populations suggest multiple manufacturing processes or batches. Dr. Webb calculated the probability of natural formation producing this distribution. Assuming generous parameters for natural sphere-forming processes, the odds of seeing 3 distinct-sized populations with this degree of separation is approximately 1 in 12,000, not impossible, but highly improbable. Add in the compositional complexity and uniform shapes, and the probability of natural origin drops below 1%. The most disturbing findings from Glen Etive 2 came from Curiosity's dynamic albedo of neutrons, DAN instrument, and radiation detectors. These instruments monitor neutron and gamma-ray emissions from the Martian subsurface, data that reveals the presence of hydrogen, potential water, and various radioactive elements. During and immediately after the drilling at Glen Etive 2, Dan detected radiation signatures that should not exist on Mars's surface. Specifically, the instrument recorded gamma-ray emissions with energies corresponding to specific radioactive isotopes: cesium-137, strontium-90, and plutonium-239. These isotopes don't occur naturally in significant quantities. Cesium-137 and strontium-90 are fission products, created when uranium or plutonium atoms split in nuclear reactors or weapons. Plutonium-239 is primarily artificial, produced in nuclear reactors. Their presence on Mars in concentrations above background levels requires explanation. Dr. Maria Gonzalez, a nuclear physicist at Los Alamos National Laboratory, reviewed the radiation data through a collaboration agreement with NASA. Her findings were classified, but elements leaked through academic channels. The isotope ratios we detected are consistent with nuclear weapons testing or reactor waste. The ratio of cesium-137 to strontium-90 matches the signature from plutonium-based fission devices, and the plutonium-239 concentration, while low, is approximately 1,000 times higher than natural Martian background. The half-life of these isotopes provides a timeline. Cesium-137 has a half-life of 30 years. Strontium-90's half-life is 29 years. If these isotopes were created by nuclear reactions on Mars, they've been decaying ever since. Working backward from the detected concentrations, scientists can estimate when the nuclear event occurred. Dr. Gonzalez's leaked calculations suggested a timeline of 170, 190 million years ago, assuming the isotopes were created in concentrations similar to those produced by terrestrial nuclear weapons. If the original concentrations were higher, the timeline extends proportionally. This date is significant. 180 million years ago, Mars was already a cold, dry world with a thin atmosphere, but it hadn't always been that way. Evidence from Martian meteorites and orbital observations suggests Mars lost most of its atmosphere in a catastrophic event or series of events between 3.8 and 4.1 billion years ago. But other evidence points to more recent water activity. Some Martian gullies show features suggesting liquid water flow within the past few million years. And certain regions display geological features, like the glass deposits in the Medusae Fossae Formation, that appear much younger than Mars' ancient past. The presence of anthropogenic radioactive isotopes suggests technological activity on Mars within the past 200 million years. Whether this represents native Martian civilization, visitors from elsewhere, or something else entirely remains unknown. The most mysterious aspect of the Glen Etive 2 incident is what happened after the drilling stopped. For 3 days, 72 hours, Curiosity went silent. No routine telemetry, no status updates, no imagery. The rover simply stopped communicating. NASA's official explanation: a software anomaly required the rover to reboot its main computer and re-establish its autonomous science protocols. During this time, data was stored in onboard memory but not transmitted. But mission controllers who worked during this period tell a different story. Dr. Robert Malhotra, who served as a mission planner for Curiosity from 2014 to 2021, spoke anonymously about the incident. The 3-day silence wasn't a software problem. The rover was receiving commands. We could see acknowledgement signals in the downlink, but the response data wasn't routine telemetry. Curiosity was sending encrypted data packets using protocols we'd never seen before. Someone, somewhere in the mission team, was communicating with the rover through channels that bypassed normal mission operations. The encrypted transmissions raised immediate red flags. Curiosity's communication systems weren't designed for encryption beyond basic error correction coding. Yet the signal structures detected during the 3-day silence showed characteristics of advanced encryption, frequency hopping patterns, burst transmissions, and encoding schemes inconsistent with NASA's standard protocols. It looked like military communications, Dr. Malhotra stated. Secure, compartmented, designed to prevent interception and analysis. The only explanation is that someone had prepared alternative communication pathways in advance, installed in Curiosity's software without most of the mission team knowing about it. The implications are disturbing. If a subset of the Curiosity team had the capability to commandeer the rover and communicate through hidden channels, it suggests planning and intentionality. They knew, or at least suspected, that the mission might discover something requiring secure communication and response protocols beyond standard scientific operations. When Curiosity resumed normal communications on September 27, 2019, it had moved 47 meters from the Glen Etive 2 drill site. Mission logs show no commanded movements during the silence period, yet the rover had relocated itself. Someone or something had commanded Curiosity to leave the discovery site and resume normal operations elsewhere. The drill at Glen Etive 2 was never photographed again. The site doesn't appear in any subsequent imaging passes. It's as if mission planners deliberately avoided looking back at the location where Curiosity made its most significant discovery. Glen Etive 2 wasn't the first time Curiosity encountered anomalous findings that were subsequently downplayed or ignored. Throughout its mission, the rover has documented features that challenge conventional understanding of Mars's history. In 2014, Curiosity photographed what appears to be a manufactured object partially buried in sediment, a metallic-looking component with right angles and regular geometric features, completely unlike the surrounding rocks. The image was released in a data dump of thousands of routine photographs, received no official comment, and has been largely forgotten, except in fringe research communities. In 2017, the rover's ChemCam detected organic molecules in concentrations far higher than expected in ancient Martian sediments. The discovery was announced with careful hedging, complex organic chemistry rather than organic compounds. But analysis of the spectroscopic data revealed structures consistent with chlorobenzene and other aromatic hydrocarbons more commonly associated with industrial processes than natural organic chemistry. In 2018, Curiosity detected a methane spike 10 times higher than normal background levels. Methane on Mars is controversial because it could indicate biological activity. The spike appeared suddenly, persisted for several weeks, then vanished. NASA described it as an interesting atmospheric phenomenon requiring further investigation. No follow-up investigation was announced publicly. Dr. Torres identified a pattern in how these anomalous findings are handled. There's a protocol, unofficial but consistent. When Curiosity detects something genuinely anomalous, the initial data is released quietly in massive data dumps, where it gets lost among thousands of routine images and measurements. Public statements emphasize caution and the need for further study. Then the topic is dropped. Follow-up investigations either don't happen or aren't publicized. The Glen Etive 2 incident fits this pattern perfectly. The drilling operation received no real-time public updates despite being one of the most ambitious of the mission. The subsequent data release was fragmentary and heavily curated. And when questions arose, NASA's response emphasized technical complications and ongoing analysis, rather than discussing the scientific findings. But Glen Etive 2 is different in scale. Previous anomalies could be explained away as instrumental artifacts, measurement errors, or misinterpretations of complex data. Drilling into a cavity containing manufactured spheres and radioactive isotopes consistent with nuclear technology leaves far less room for alternative explanations. If artificial materials and nuclear signatures really exist beneath Mars's surface at Glen Etive 2, when were they created? And by whom? The standard narrative of Mars's history describes a planet that was warm and wet billions of years ago, with a thick atmosphere and possibly oceans. But around 4 billion years ago, Mars lost its magnetic field, allowing solar wind to strip away most of its atmosphere. The surface became cold and dry, and any life that might have evolved either went extinct or retreated underground. But evidence has been accumulating that challenges this simple narrative. Some Martian features appear far younger than they should. Glass deposits in various locations show formation ages of only a few 100 million years. Impossible if Mars has been geologically dead for billions of years. Dr. John Brandenburg, a plasma physicist who has studied Mars's atmospheric history, proposed a controversial hypothesis that Mars experienced a nuclear catastrophe that destroyed a surface civilization and altered the planet's climate. His theory, based on analysis of Martian atmospheric isotope ratios and surface features, suggests two large nuclear explosions occurred in Mars's northern hemisphere, creating the radiation signatures and glass deposits we observe today. The isotope ratios in Mars's atmosphere show evidence of massive nuclear detonations, Dr. Brandenburg stated in his research. The concentrations of xenon-129 and other heavy isotopes are consistent with nuclear weapons effects. Additionally, thin layers of radioactive potassium, thorium, and uranium appear globally distributed as if they were lofted into the atmosphere and settled out across the planet. Brandenburg's hypothesis places these events around 180 million years ago, remarkably consistent with the timeline suggested by the radioactive isotopes detected at Glen Etive 2. But who would have detonated nuclear weapons on Mars? Three possibilities emerge. First, indigenous Martian civilization. Life arose on Mars during its warm, wet period, evolved intelligence, developed technology, and destroyed itself through nuclear warfare. The survivors either went extinct or fled underground, leaving behind ruins and artifacts that erosion has slowly buried. Second, external civilization. Visitors from another world, perhaps Earth itself, if terrestrial intelligence is older than we recognize, or another solar system entirely, established a presence on Mars, engaged in conflict or catastrophic accident, and departed, leaving contamination behind. Third, weapons testing. An advanced civilization used Mars as a testing ground for nuclear or more exotic weapons, deliberately choosing a dead or dying world to avoid collateral damage to inhabited planets. Each scenario has implications that challenge our understanding of life's history in the solar system and the prevalence of intelligent technological civilizations. If curiosity really did drill into artificial structures containing nuclear signatures, why would NASA cover it up? What possible justification exists for withholding such momentous discoveries? Several explanations have been proposed, ranging from prosaic to paranoid. Verification before announcement. NASA might legitimately want to confirm extraordinary findings through multiple independent analyses before making public statements. Premature announcements of life-related discoveries have embarrassed the agency before. The 1996 announcement of possible Martian fossils and meteorite ALH 4001 was later largely debunked. Perhaps NASA learned to be more cautious. National security concerns. If the findings suggest advanced technology, military and intelligence agencies might classify the information. Technologies capable of producing refined metals and nuclear materials on Mars could have strategic implications for space exploration and national security. Control of such information might be deemed necessary by authorities beyond NASA's civilian mission. Societal impact assessment. The discovery of evidence for previous intelligent civilizations would have profound philosophical, religious, and social implications. Governments might want time to prepare public statements, brief religious leaders, and assess potential impacts before making announcements. Planetary protection protocols. If artificial structures exist beneath Mars's surface, contaminating them with Earth microbes carried on Curiosity could damage invaluable evidence. NASA might be withholding information while planning follow-up missions with proper sterilization and contamination prevention protocols. Private sector involvement. Some researchers have suggested that commercial space companies might have been briefed on the findings and are planning proprietary missions to investigate further. Withholding information could provide first-mover advantages in accessing or exploiting whatever exists beneath Mars's surface. Dr. Patel takes a cynical view. Once you've made the decision to withhold information, maintaining that secrecy becomes self-sustaining. Admitting the cover-up becomes more damaging than continuing it. If NASA has been sitting on evidence of artificial structures on Mars for 6 years, they can't simply release it now without explaining why they waited. The institutional incentive is to keep waiting, keep denying, and hope nobody pieces together enough evidence to force disclosure. Curiosity's successor, the Perseverance rover, landed in Jezero Crater on February 18, 2021, less than 18 months after the Glen Etive 2 incident. Perseverance carries upgraded instruments, better cameras, and crucially, the capability to cache samples for eventual return to Earth. The mission's stated objective is to search for signs of ancient microbial life. But some researchers believe Perseverance's true mission was shaped by what Curiosity found. Jezero Crater was selected as the landing site years before Perseverance launched, but the specific investigation targets within the crater have evolved during the mission, and some of those targets show characteristics remarkably similar to Glen Etive 2. In July 2023, Perseverance investigated a region called Hog Wallow Flats, where ground-penetrating radar detected subsurface density anomalies. The rover conducted extensive imaging, but notably did not drill. After several weeks of investigation, Perseverance moved to a different location without collecting samples. The decision puzzled the mission science team. Dr. Chen, who now works on Perseverance's ground-penetrating radar analysis, described the situation. Hog Wallow Flats showed every indication of being scientifically valuable. The mineralogy was complex, the stratigraphy was well preserved, and the radar data suggested interesting structures below the surface. But mission planners decided to skip it after preliminary investigation. The official explanation was that other targets offered better science return, but many of us wondered if there were other considerations. In September 2024, Perseverance encountered another anomaly. While drilling at a site called Bunsen Peak, the rover's instruments detected spectral signatures similar to those reported from Glen Etive 2, refined metal signatures inconsistent with natural Martian geology. This time, rather than continuing investigation, Perseverance immediately retracted its drill and moved away within hours. No official explanation was provided. Mission updates made no mention of the anomalous readings, and unlike Curiosity's extensive data transmission from Glen Etive 2, Perseverance's telemetry from Bunsen Peak was minimal. They learned from Curiosity, Dr. Malhotra suggested. The Glen Etive 2 incident taught them that extensive investigation generates data that's hard to suppress completely. Better to detect the anomaly, note the location, and move on quickly. Future missions can investigate more carefully with better compartmentalization. This raises a disturbing possibility that multiple locations on Mars contain similar anomalies: artificial materials, nuclear signatures, manufactured structures. If the discoveries at Glen Etive 2 represent not a unique site, but one example of a widespread phenomenon, It would explain NASA's caution and compartmentalization. NASA's Mars Sample Return mission, currently scheduled for the early 2030s, will retrieve rock samples cached by Perseverance and bring them to Earth for detailed analysis. The mission is one of the most ambitious and expensive planetary science efforts ever attempted, with costs approaching $10 billion. What's rarely discussed publicly, the mission architecture includes contingencies for handling atypical samples that might require special containment or security measures beyond standard planetary protection protocols. Dr. Torres reviewed the mission's technical documentation. The sample return container has capabilities that go far beyond preventing microbial contamination. It includes shielding for radioactive materials, reinforced containment for chemically reactive substances, and even provisions for samples that might be technically sensitive from a national security perspective. Why would a mission designed to return ancient Martian rocks need radiation shielding and security provisions? The official explanation emphasizes caution regarding unknown Martian chemistry and the slim possibility of discovering radioactive minerals. But the specifications seem excessive for natural geological samples, unless NASA is planning to return samples that aren't purely natural geological materials. If Perseverance has identified multiple locations with artificial materials, the mission planners would want the capability to return those samples to Earth safely and securely. Dr. Patel noted, "You can't simply announce that you're building a spacecraft to return alien artifacts. That would create public panic and political complications. Better to design the capabilities into the mission quietly, described in technical terms that don't raise questions." The Mars Sample Return mission includes another unusual feature. The samples will initially be delivered to a high-security Biosafety Level 4, BSL-4, facility, the highest level of biological containment, typically used for deadly pathogens like Ebola. While justified under planetary protection protocols, the security measures exceed what would be necessary for sterile Martian rocks. Unless they're planning to study samples that might contain active technology, Dr. Malhotra suggested. If you're going to analyze microscopic manufactured spheres or components of ancient machinery, you'd want the same kind of secure, contained environment, not because they're biologically dangerous, but because you want complete control over who has access and what information gets released. On September 24, 2019, NASA's Curiosity rover drilled into the Martian surface and encountered something that wasn't supposed to be there. The evidence, what little has been released, points to manufactured materials, nuclear signatures, and engineered structures buried beneath the red sands of Gale Crater. For 47 hours, Curiosity transmitted massive volumes of data back to Earth, capturing images and measurements of a discovery that could rewrite the history of intelligence in our solar system. Then came 3 days of silence, during which the rover moved away from the site and resumed normal operations as if nothing extraordinary had occurred. 6 years later, we're left with fragments, released images showing microscopic spheres too uniform to be natural, spectroscopic data suggesting refined metals and alloys, radiation signatures consistent with nuclear technology, and an official narrative that emphasizes interesting mineralogy, while avoiding the obvious implications of the evidence. Was Glen Etive 2 a time capsule, a deliberately preserved repository of materials meant to be discovered by future explorers? Was it a waste site, the discarded remnants of nuclear technology used by an ancient Martian civilization? Or was it something else entirely, evidence of visitors who came to Mars long ago, used the planet for purposes we can only guess, and left behind traces we're only now beginning to find? The truth remains buried beneath layers of Martian soil and institutional secrecy. But the evidence that has emerged suggests we're not looking at random geological curiosities. We're looking at artifacts, proof that Mars has not always been as dead and empty as we assumed, evidence that technology once operated on the red planet's surface or beneath it, leaving signatures that persist across millions of years. Curiosity stopped drilling at Glen Etive 2 not because of technical difficulties or random scientific decisions. It stopped because of what it found. And that discovery was significant enough to trigger protocols that most of the mission team didn't know existed. Secure communications, data compartmentalization, and immediate extraction from the discovery site. The rover continues its mission today, climbing Mount Sharp, drilling at new locations, searching for evidence of ancient water and habitable conditions. But it has never returned to Glen Etive 2. The site remains undisturbed, its secrets preserved beneath the Martian surface, waiting for a mission that will eventually come to investigate properly, a mission that will be designed from the start to handle discoveries too significant for routine scientific protocols. Until then, we're left with questions. What else lies beneath Mars's surface? How many other locations contain similar anomalies? And what will we find when we finally have the courage and capability to excavate these sites properly and bring their contents home for analysis in laboratories designed not for studying rocks, but for understanding artifacts? The Mars time capsule at Glen Etive 2 has changed everything, even if most of the world doesn't know it yet. Because if artificial materials exist at one location on Mars, they likely exist at others. If nuclear signatures appear in one drill core, similar signatures probably wait in undiscovered deposits across the planet. And if Curiosity found evidence of technology operating on Mars within the past 200 million years, then the solar system's history is far richer and more complex than we ever imagined. The red planet holds its secret still, buried in the regolith of ancient craters and beneath the sedimentary layers of dead ocean beds. But those secrets are beginning to emerge, one drill hole at a time, one fragment of data at a time, one whispered revelation from mission scientists who wonder if the public deserves to know what's really up there. And perhaps one day, when the evidence becomes too overwhelming to suppress, we'll finally learn what Curiosity discovered on that September day in 2019, what lay beneath the surface at Glen Etive 2, and what it means for humanity's understanding of our cosmic neighborhood and the ancient invisible history that surrounds us. The drilling stopped, but the truth is still waiting to be uncovered.